Android, developed by Google, is a widely adopted mobile operating system. It powers a diverse range of devices, from smartphones and tablets to wearables and smart TVs. Its open-source nature and versatility have contributed to its immense popularity. Security is a paramount concern in the mobile landscape, given the sensitive data these devices handle. Android incorporates a multi-layered security architecture to address these concerns. It aims to protect user data, preserve system integrity, and provide a trustworthy mobile experience. Android's security model is built on a foundation of well-established principles. These include sandboxing, access control, and secure communication channels. These principles are implemented through a combination of architectural components and software features. Understanding these features is essential for both users and developers. This knowledge empowers users to make informed decisions about their privacy. It enables developers to create secure and reliable applications. Android's architecture is designed in a layered manner, which is both strategic and functional. Each layer serves a specific purpose and interacts with the layers above and below it, creating a cohesive and efficient system. This layered approach enhances security by providing isolation and abstraction, making it harder for malicious software to penetrate the system. At the core of the Android system lies the Linux kernel, which is fundamental to its operation. This kernel manages the system's resources, such as memory and processing power, and provides essential services that other layers rely on. It acts as a bridge between the hardware and the software, ensuring seamless communication and functionality. The kernel enforces security policies through mechanisms like user IDs and permissions, which control access to system resources. Above the Linux kernel sits the hardware abstraction layer, or HAL, which is crucial for hardware management. This layer provides a standardized interface for accessing hardware components, making development easier and more consistent. The HAL isolates the operating system from hardware-specific details, allowing for greater flexibility and compatibility. This isolation enhances portability and limits the impact of potential hardware vulnerabilities, ensuring a more secure system. The Android runtime, or ART, is a crucial component responsible for executing Android applications, translating code into actions. It provides a managed environment that ensures apps run safely and efficiently, optimizing performance and security for users. RT plays a pivotal role in maintaining Android security. It introduces several security features that protect both user data and the system's integrity. One of RT's key contributions is its ahead-of-time, or AOT, compilation. In this process, app code is compiled into native machine code when an app is installed. This AOT compilation enhances performance and security by reducing the attack surface during runtime. ART also incorporates a robust memory management system. This system prevents apps from accessing each other's memory. This isolation is crucial for preventing data leaks and malicious code injection. Another important feature of ART is its support for sandboxing. Each Android app runs in its own isolated sandbox. This sandbox restricts the app's access to system resources and other apps' data. Even if an app is compromised, the sandbox limits the potential damage it can cause. The Android application framework provides a rich set of tools and APIs for app development. It includes components for creating user interfaces, accessing data, networking, and more. The framework is designed to guide developers towards secure coding practices. Android encourages developers to follow the principle of least privilege. Apps should only request the permissions they need to function correctly. This minimizes the potential impact if an app is compromised. The framework also provides mechanisms for secure data storage. Developers can use internal storage, external storage, or content providers to store data securely. Internal storage is private to the app, while external storage is accessible to other apps and the user. Content providers offer a structured way to share data between apps. The Android framework facilitates secure communication between apps and external servers. It supports industry-standard protocols such as HTTPS for encrypted communication. Section 5, Sandboxing. Sandboxing is a fundamental security principle in Android designed to protect your data and privacy. It involves isolating each app within its own restricted environment, ensuring they operate independently. Think of it like each app running in its own little container. separate from others. This isolation prevents apps from interfering with each other or accessing data they shouldn't, maintaining integrity. Each app runs with a unique user ID and group ID, which are crucial for security. These IDs determine the app's access rights to system resources and files, ensuring proper permissions. Apps cannot directly access the files or data of other apps, creating a secure environment. Communication between apps and with the system is carefully controlled, minimizing risks. Apps can only interact with each other or the system through well-defined interfaces, known as APIs. This controlled communication prevents malicious apps from hijacking or manipulating other apps, safeguarding your device. Sandboxing significantly enhances Android's security posture, making it robust against threats. It limits the potential damage of compromised apps containing threats effectively. It ensures that even if one app is compromised, other apps and the system remain protected, maintaining overall security. Section 6. Secure communication between apps, IPC, and its role. Inter-process communication, or IPC, mechanisms enable apps to communicate with each other. This communication is essential for various tasks, such as sharing data or accessing services. Android provides several IPC mechanisms, each with its own security considerations. One common mechanism is intents. Intents are messages that apps can send to each other. The system ensures that the receiving app has the necessary permissions to handle the intent. Another mechanism is services. Services are background components that can perform long-term operations. Apps can bind to services to interact with them. Android enforces access control on services. Only authorized apps can bind to and communicate with a service. Content providers offer a structured mechanism for sharing data between apps. Apps can define rules for accessing and modifying their data through content providers. Section 7. App permissions. Controlling access to sensitive data. App permissions play a crucial role in protecting user privacy and data security in Android. When an app needs to access sensitive information or perform potentially risky actions, it must request permission from the user. Permissions are categorized based on the type of access they grant. Some permissions are considered normal and are granted automatically. Others are considered dangerous and require explicit user approval. Users have granular control over app permissions. They can grant or revoke permissions for individual apps through the system settings. Android has evolved its permission model over time to enhance user privacy. Earlier versions of Android used a static permission model. Apps requested all the permissions they needed at install time. Newer versions introduced a dynamic permission model. Apps request permissions only when they are needed during runtime. Section 8. Booting up securely the Android boot process. The Android boot process is a critical phase that involves loading the operating system and initializing the device. This process is essential for the proper functioning of the device and ensures that all necessary components are correctly loaded. Security is paramount during this process to ensure that the device boots into a trusted state. Without these security measures, the device could be vulnerable to various threats and attacks. The boot process involves several stages, each with its own security checks. These stages are designed to verify the integrity and authenticity of the software being loaded. It starts with the bootloader, a small program that verifies the integrity of the operating system before loading it. The bootloader is the first piece of code that runs when the device is powered on. The bootloader uses cryptographic signatures to ensure that the operating system hasn't been tampered with. These signatures are crucial for maintaining the security and integrity of the device. Once the operating system is loaded, the kernel takes over. The kernel is the core component of the operating system, responsible for managing hardware and system resources. The kernel verifies the integrity of itself and other critical components. This step is vital to ensure that no malicious code has been introduced into the system. It mounts the file systems in a secure manner, enforcing access control policies. These policies help protect sensitive data and prevent unauthorized access. The init process, launched by the kernel, starts essential system services and applications. This process is responsible for initializing the user space and setting up the environment for the user. The boot process ensures that only trusted code is executed. This is achieved through a series of checks and verifications that occur throughout the boot sequence. It sets the foundation for a secure Android environment. By ensuring that the device boots securely, users can trust that their data and applications are protected from potential threats. Section 9, Conclusion, a secure foundation for mobile experiences. Android's security model is built on a foundation of layered architecture, sandboxing, access control, and secure communication. The Android runtime, or ART, enforces memory safety and app isolation. The application framework provides tools for secure app development. The principle of least privilege guides developers in minimizing app permissions. IPC mechanisms enable secure communication between apps. The boot process ensures that the device starts in a trusted state. These security features work together to protect user data, preserve system integrity, and provide a trustworthy mobile experience.